Okay. Hi, I am Hannaneh Hajishirzi. This is unfortunate that my student couldn't make it to the conference because of visa issues, so I'm presenting this work on learning to solve math word problems using verb categorization. And this is a joint work with Oren Etzioni and Kushman. Designing algorithms that can automatically solve math and science problems have been a long-standing AI challenge since very early days of AI. In particular, it's interesting for natural language processing because usually the texts are concise and their semantics can be represented with some simple algebraic equations. So for example, in this story that you see on the board, we can represent it with these equations like 9 minus x equals 5, right? And the number of kittens is equal to 4. It's usually challenging for children to solve these problems, mostly because of the calculation part or because of the reasoning part. But for computers, it's hard because of the language processing part. This is challenging because we have a lot of problems in a variety of domains and across many different tasks. So for instance, we have some problems about science experiments, we have some problems on shopping, we have some problems on everyday life, right? So these problems are usually designed at the level of child's word knowledge, and there is usually no constraint on the syntax or vocabulary. So for instance, look at this story. There were 7 million people living in a country. Last year, 90,000 children were born and 16,000 people immigrated to that country. To be able to answer the question of how many people began living in that country, we need to know that we should sum the number of children who were born and the number of people immigrated to that country. There are some parts of the question that we really don't care about. So for example, you can easily replace the word kitten with something else like toy aircrafts or cookies or books, right? And the story wouldn't change and the final equation also wouldn't change. But at the same time, if you replace some words, in particular verbs, with another verb, then the whole story will be different and the final equation will be completely different. Right? So for example, if you replace the verb give with receive, then we have a different equation. While verbs play a crucial role in understanding these stories, there are some parts of the sentences that are completely irrelevant. So for example, knowing that 3 of kittens have spots really doesn't matter in forming the final equation. Or even this extra information, like John now has 11 kittens, doesn't matter, right? So there are also some parts of the question that are missing, right? So we have irrelevant information and missing information. So look at this story. There were 6 roses in a vase. Mary caught some more roses from her flower garden. There are now 16 roses in the vase. We never have received this information that the roses caught from the flower garden have been put in the vase. Right? So there are some missing information involved in these stories. So verbs play a crucial role in understanding these stories and forming these final equations, but at the same time, they are ambiguous. For example, look at the verb lost here. In the first story, Sarah's high school won 5 basketball games and they lost 3 games. We need to translate this verb lose to an addition operation, right? Because to be able to understand the total number of games, we need to sum over lost and win games. But for the next story, John has 8 orange balloons but lost 3 balloons. We need to do a subtraction. We need to translate the verb lose to a subtraction. So to be able to understand these stories, we really need to incorporate the context. And we basically need to understand these sentences and put them in a context and form the final equation. So we can't analyze each sentence individually and in isolation from the rest. So basically the problem that we are addressing here is to solve arithmetic word problems that include additions and subtractions. And our goal is to translate them to algebraic equations. Usually these word problems describe a partial world state, and then by adding more and more sentences, they either elaborate the current world state or add some updates to it, right? And then these problems will end with one question that asks about the quantity of some entity. The way that we address this problem is to make a state space representation. To be able to abstract from the problem text, we represent it in this form of a state representation that Liz has 9 kittens. And then with observing new sentences and basically new verbs, we make the state transitions. So for example, the verb give tells us that the quantities of kittens is changed in the Liz, count for Liz, and then the kittens have been added to John. Right? So this is our main intuition, that we want to make a state space representation, update the states based on the categories of verbs, and then finally do inference and form the final equations. There has been previous work in the literature. Actually, our work is in part similar to language grounding, where the idea is to translate sentences to events and entities and also finding out their relationships. But most previous work usually look at these sentences in isolation from the others and don't look at the whole context. Also, there has been previous work in solving math word problems. Earlier systems were most rule-based, and they were trying to use manually annotated rules to solve these problems. Most recently, at ACL 2014, there was another work on learning to solve math word problems by translating these problems into template equations. They could handle more math problems, but it was harder to generalize to more problem types, meaning that they were less robust to diversity of problem types across training and test. So the way that we represent these problems is actually this state space representation. Or more formally, what we do, we represent the quantities of entities inside each container. Basically, we look at the sentence, Liz has 9 black kittens, and update S0 to S1, which includes these quantities. Entities are discrete objects whose quantities are changing over time, like kitten in our example, and they usually have some associated attributes and also numbers. Like black is the attribute of the kitten, and also we have 9 kittens. And then containers are holders of sets of entities. For example, Liz and John in our particular example. Then sentence fragments shows transitions between states. They are either observations that they give some elaborations of the world state, like Liz has 9 black kittens, or some updates showing that the quantities are changing in the containers. Like Liz gave some of her kittens to John. We model these transitions based on verb categories. For example, the verb give is a negative transfer verb, shows the transfer of quantities from Liz to John. And then we update the quantities of kitten for Liz, we decrease them, and we increase the quantities of kitten for John after this action. Verb categories are actually defined based on how the quantities are changing in one container, in the containers of the sentences, and we have their different verb categories, including positive and negative transfers, or construction or destruction, and also initializations. Here is the outline of our method. We first look at the sentences, ground them into entities and containers and verbs, and then do training and learn verb categories, And at test time, we perform an inference, update our state transitions, and form the final equations. How do we ground the entities? We basically run deterministic rules on top of an output of a dependency and a constituency parser. In particular, we select entities as noun types that are modified by a number in our story, like a kitten in here. Then we extract the quantities that are associated with these entities, like 9, 3, 11, and 5. We select the attributes as adjective or noun modifiers of these entities, and we also list their verbs. Then for every sentence fragment that we've come up with, we try to find one or two containers. The first container is the subject of the sentence, and the second container is either the direct object or an adverbial phrase. We also want to deal with missing information, and the way that we handle it is to use a circumscription assumption, where the idea is that the set of containers are fixed in our problem set. And this way, we know that the roses that are cut from the flower garden have been put in the vase because we have a fixed set of containers. So after this step, we have translated every sentence into this form: the verb, the quantity, entity, and one or two containers. Now our goal is to learn the verb categories. For example, we want to know that give is actually a negative transfer verb. And the way that we model it is with binary classification. We want to know that it's going to be increasing for the first container list, and it's going to be decreasing for the first container and increasing for the second container. Basically, our goal is to do binary classifications for every verb of the sentence and each of the containers. We extract and download some problems from the internet, and we divide them into training and test. But we make sure that similar problem types won't appear at training and test. Similar problem types won't appear in both training and test. And also we make sure that no verb is repeating from train and test. Then we train binary classifiers to see the label of every verb corresponding to each container. To be able to generalize to new problem types, we don't use lexical features, and we use similarity-based features and also some clues from the structure of the sentence. The most important features for training are our similarity-based features, where the idea is to look at the verb of a sentence, give, and compute their similarity, which is a simple linear similarity in our case, to a list of seed verbs. These seed verbs are selected such that we have some representatives for each category. So for example, we have some verbs for negative transfer, we have some verbs for constructions, and so on. And we have designed a method that we can automatically select these seed verbs. I don't go into the details, we can discuss them offline, but the idea is that we define a classification task, and we select these verbs out of 2,000 most common verbs of English, and we do a simple feature classification to be able to select those verbs, such that they are the most discriminative for one particular category. Also, we take advantage of structural features. For example, look at these two sentences. Alice paid $5 to the rental shop. She gave some of her kittens to John. These two sentences are semantically different, but their structure is similar, right? And they both show some sort of negative transfer. To be able to model this, we use dependency parse relationships from the verb of a sentence and the other words. We also take advantage of WordNet verb senses. For example, WordNet have some senses like possession, creation, construction, and we have included those also in our feature vector. So now we have trained our classification task, and at the end of this, we would be able to predict verb categories at test time. So now, given we know the verb categories, we want to update and build these state transitions. And the idea is as follows. We have our sentences in the story. At the beginning, we build the grounding entities, the containers and verbs, and now we are using our predictions. So for example, we predict that has is an initialization verb. Therefore, we update the state of the world as follows. We put 9 kittens in the Liz container. And then we look at the next sentence. Give is a negative transfer. It increases the quantities for Liz, for John, and decreases the quantities for Liz. So we update these equations. And we also continue build the whole state representation for the whole problem. And we also are careful to select sentences that are related to the question entity. And finally, we form equations. The way that we form equations is to look at the question sentence, align the question entity, the corresponding container, and also the verb of the sentence. And we find where the question is asking about. It can be about the initial state, last state, or some of these intermediate states. So for instance, in our problem, how many kittens did John get? We are asking about this intermediate state, right? And given that, we form the equations. How do we do that? We find the first variable that includes an unknown quantity, 9 minus L1 here, basically the next state. And also we look for the next state that has known quantities of the kittens, which is 5 over there at the status 4. And we put them in correspondence and finally build a final equation. To evaluate our method, we downloaded different data sets from different websites. Each data set includes addition and subtraction problems, but they have different characteristics. MA1 is the most straightforward data. IXL has more complicated sentences and also includes a lot of missing information. And MA2 includes a lot of irrelevant information. Then we evaluated our method on 2 tasks of solving word problems and also verb categorization. This first graph shows the accuracy of our method as you see the x-axis on different data sets. We compared this with the previous work from the ACL 2014, and for this set of experiments, what we did was to train on 2 data sets and test it on the 3rd one to make sure that we are robust to diversity of problem types. So as you see, look at the total number, we significantly outperform Kushman et al.'s work. And as you see here, the most gain that we observe is from these 2 data sets that included missing information and irrelevant data. We also evaluated our method on verb categorization and compared it with 2 baselines. One which is majority baselines that uses the most frequent verb sense, and also a WordNet baseline that uses the WordNet verb senses. And as you see, the blue line shows the accuracy of our method in verb categorization and also solution. And as you see, we significantly outperform in both baselines. We also performed an ablation study and wanted to study the effect of features in our classification task. As expected, removing the similarity-based features had the most effect. This red line shows the highest decrease in our performance, and also the other features also play an important role. Also, to understand the limits of our method, we compare the performance of ARIS, the red line, the full system, with gold ARIS, which in which we use the gold standard verb categories. Basically, we assume that we know the correct verb categories and just try to solve problems based on those gold verb categories. So look at these results. In the first data set, the most straightforward one, we kind of aced, right? We got about 95% accuracy. But in 2 other data sets, we got somewhere around 80 to 83%, which means that there is still a lot of room for more improvement. We performed some error analysis on the gold areas, basically to understand what's going on and what are the different problems. The first and most important category of errors come from lack of prior knowledge. So look at this story. Tom bought a skateboard and spent this much dollar on marbles and some on shorts. How much did he spend on toys? So our method wasn't able to know that shorts is not a kind of toys, right? So we mistakenly summed all the numbers. Also, our method has been built on top of the current parsing and co-reference resolution systems. So there are a big portion of errors due to the parsing issues. Like here, we couldn't do correct co-reference resolution. And also, we have some errors in compositional semantics. Here I show you a simple form, like in March it rained 81 inches, it rained 35% less inch in April than in March. So parsing these type of semantics was also hard. To conclude, in this work, I presented the status space representation to model math word problems and show how can we do a state transition according to the verb categories. And we also showed that with this approach, we managed to be more robust to the diversity of problem types across training and test. And in future, what we like to do is to generalize similar ideas to more problem types that include multiplication, divisions, and simultaneous equations. Also, we like to improve the parsing and co-reference resolution modules that our system is built on. Also, we like to be able to infer or incorporate the word knowledge that we might get from this data set and from this type of problems. Thank you. Yes.
Thanks a lot for the interesting talk. So I'm wondering, I guess you showed some examples and you must have eyeballed the data set. So I'm wondering how formulaic is the actual input text? I mean, how robust is your model in terms of the order of sentences? I mean, is it very similar among different data sets or different examples?
So that's a very good question. So in the first data set, we kind of can take advantage of this sequential order of the data set. And as you see, we got about 95%, right? But in the second data set, we have some sentences that we really couldn't use this order of sentence. And this was also some part of the errors, but it was in the less kind of frequent errors. And the way that we are thinking about it is we still are able, because they are usually this relative order when they describe these narratives, right? So the way that we are thinking about right now is we use the same representation, but our goal is to add more relationships between the entities. Like, so there are some of them kind of build the hierarchies or how they are related. So.
You mentioned that you wanted to move on to cover multiplication and division. Is this just going to be a matter of adding new seed words, or are you going to have to change the state? So basically, what is it that you think you're going to need to do?
So the first actually attempt that we are making is adding more seed verbs. But we are right now very much concerned about these word knowledge that we are missing. And our goal is kind of to build, to add a little bit more to our data such that we are able to generalize these word knowledge. So basically we are not just moving these multiplication, division, but also try to be able to do more general settings.
Yeah, thanks, Hannah, for the interesting talk. Maybe I missed the part, but I'm wondering how the model works with your examples about the verb lost. So you had two examples for lost. How does it work?
So that's a very good question. So one scenario that right now we are considering is how these two verbs co-occur to each other, right? So because you always want to build and learn this verb category given the current context, right? And basically lose in one case is the category of increasing and in the other is the category of decreasing.